We have looked at metals from the standpoint of their occurrence and refining them, alloying them, producing them into various shapes, and finally getting them into service. In this series, I would like to look at the metals in service and see some problems that we have that stem primarily from just the use of the material. This has become a very important subject for many reasons, the least of which is consumer product liability claims. But one of the things that will happen in a metal is that it will fatigue. Now, I want to talk about this later on, but I want you to help me with a little experiment first. I've given each of you a paper clip, and I want you to straighten the paper clip out as straight as you can get it. And then I want you to hold it in your fingers like I am holding it in my fingers, so that your thumbnail, let's say, is against one side of the paper clip. And then I want you to bend the paper clip as far as you can and then straighten it back out and bend it again at the same spot. Now, we already know that when we do this, that the material is going to strain harden. But what I'm interested in is how many cycles it will take to fracture the material if I bend it back and forth at exactly the same spot. So I want you to continue to do that and see if you can remember the number of cycles that it took you to do it while I begin to talk to you about something else. Actually, we are interested in trying to find out, when we manufacture an article of metal, if that particular article of metal is serviceable for the use that it was intended. That is to say, we're going to consider failure as a condition when the article ceases to function in the purpose for which it was designed. And if it fails to continue to function in that way, then we're going to say, all right, the material has failed. It doesn't mean it necessarily comes into two pieces. That is, we have to look at what the design criteria was to start with. Now, when we do this, we are going to generally be interested in making a whole lot of parts. And when we look at the number of parts that we've made, we're going to say it's possible that some of these parts can have a defect in them, and some of these defects may be inherent defects that would occur. That is, we can't really control them too well, but some of the defects may be due to controllable situations. There may be human error defects in manufacturing or something like that. And so we're going to have to distinguish between the kind of defect that we have. We're going to have a system to look at the number of particles or articles, the sampling that we can do that will characterize the whole lot of material that we're making. So if we're making, say, lots of 1,000 pieces, we're going to want to find out how many of these pieces we have to take in our sampling procedure, and with the correct sampling procedure, by the way, so that we have a characteristic indication of what that entire lot looks like. And then we're going to have to make a decision on some sort of acceptance level that we will have. We're going to have to decide how many pieces that will not conform to our criteria that would cause us to reject the entire lot. And so we're going to have a little number that we're going to call a non-conforming number that is going to be a limiting number that we will accept and say if it's above this particular number, then the whole lot's no good. Well, the first thing we'll have to do is to start taking samples. Now, the exercise I've just given you is to try to get you to help me find out how many times is required to fracture the material. And so I want to see what sort of a sample I can take. Now, I'd like to ask you, how many of you, will you raise your hands now and tell me how many of you have actually been able to fracture that material with less than 5 cycles? May I see your hands? Let's see. Just 2. Now, how many of you were able to fracture the material between 5 and 10 cycles? 1, 2, 3, 4, 5, 6, 7, 8, 9. And how many of you took more than 10 cycles to fracture it? Well, we don't have any. Well, on this basis now, how many samples do you think I should take? What is the group size that I should consider to find out the number of cycles that it would took to fracture the material? Suppose I tighten up between 5 and 10. How many of you took either 6 or 7 cycles to break the wire? And we have 1, 2, 3, 4, 3. And how about 7 cycles? 1, 2. And how about 8 cycles? 1, 2, 3. And so we find that within this particular sample that I took, let's say between 5 and 10 originally, I have a spread of the data, right? Well, there are people who work hard at trying to find out the proper way to sample and the proper way to work the statistics, to control the statistics, to predict what would be an acceptable sample and what would be the criteria on this little number that we're going to have as the maximum non-conforming specimens that we will have that will cause rejection of the total lot. I'm not a quality control man. I'm not a statistician either, but I think it is interesting to look at one of the things that these people do. And what they do is pointed out in the first slide. If we're taking a measurement, in this particular case now, what we're doing is we're taking a bar of metal and we're trying to saw it into 2-inch lengths, exactly 2-inch lengths. And we're going to have a control chart in this that's going to give us some idea of how close we are coming. That says in a block of material, in a sample that we may have, which this may be this sample size now, we're going to have for each one the length of the bar, and it isn't going to be exactly 2 inches. It's going to be higher or lower than this. And within that particular frame, we're going to have an average. If we take the next sample, it may have 5 units in it, and it will have different values, and within that, we will have an average. And of course, this happens for every sample that we take, and we may have a big spread in this, and then we can take an average of all of the sample lots that we took, and we can say, we can put a line through it and get the process average if we want to. Or, as in the next slide, we can say we would like to look at, instead, the deviation from the standard that we want, and we are again trying to produce at 2 inches, but for each sample that we take in the lot, we're going to take the highest point and the lowest point and look at the difference between them. So plotted out on this particular axis now, we find that we're going to have the range, not the average, but the range over which the error will occur. So the very first specimen had a range. The difference between the lowest in that sample and the one that we're looking at would be this particular value. The second one would be that value. The third one would be this value. The fourth one that value. And the fifth one this value. So we're going to have a range number that's going to tell us what the variation was in the sample we took. And we're also going to have an average for the range for the entire sample that we took in the lot. Well, using these particular parameters, the quality control people say, we would like to have some formulation of some kind that would give us an indication of what would be an acceptable criteria for the lot. That is, how many pieces that would not conform some level, that would be outside of what they accepted in the range. How many pieces would be outside of that range that we would accept that would be non-conforming before we say the lot's no good? And so they make some assumptions, they develop some assumptions, and they develop a series of curves based on these assumptions. And the next slide shows you what one of the curves looks like for the data that I just presented, in fact. And in this particular situation, and this is called an operating characteristic curve, we have 3 curves that are presented. Now, they're really looking at the probability of acceptance. And in the 3 curves that we look at, and this is the percent, by the way, of the samples that we take of the number in the total lot. So it would have a 2% sample or a 4% sample. That's just numerically the percentage of the total lot that we would have. And here they have a case where the total lot is 50, and the number that we have, the little n is the sample size, is 5. And the value that we're going to take as the number that we will have allowed as a maximum number in that particular lot before we have complete rejection, and we're going to take it as 0. That is, we're not going to have any accepted unless they all fit, is what it's going to say. And so to get 100% probability of acceptance, it's 0, and we'd have to be at this particular level. Now what the chart really shows us is this, that if we had, say, 200 articles or particles or units in our lot, and we're on this particular curve, and let's suppose we had 4 as a sample. We took 4 pieces out as a sample. Well, that means that we would have a 2% sample, and that would say then for this particular curve at a 2% sample, we would be up on the curve at that particular point. We would have about 60, I don't know what it is, 65, 67, or something like that, percent probability that we would reject the lot. Let's find out what would happen now if we took a smaller lot size, and the lot size is 50. And if we took a lot size of 50 and the number of our samples was 5 in this particular case, then we would still have 2%, and we would be way up on this curve, and there would be a 90% probability that we are going to have the lot accepted. So what the curves tell the people in statistical and quality control is, if this is the model, if these are the characteristic curves and the criteria that we want to accept, then it would be much better to have a small lot, inspect a small lot with a 2% sample than it would be to accept a big lot with a 2% sample. And so using such devices, they come up with curves that would be ideal curve, and in an ideal curve, what you want to do, they call it a Z-type curve, but it's going to be a curve in which we have about the same percentage as the percentage that will give us a probability of acceptance. If we have an acceptance level, for instance, in this particular case, that would be 90%, then we find that if we just took 2% sample in the material, we would generally always pass the lot. And there are a number of model curves like this, and in the next slide we see another type curve that we could develop.
Failure occurs when the material no longer functions as it was designed to. When evaluating defects that do occur, it must be determined if they can be controlled, and if so, at what cost. Sampling procedures aim at obtaining a fair representation of the population, which is essential in determining acceptable defect frequencies. Sample results can be evaluated based on results averages or on range deviation. Operating characteristic curves show probabilities of samples being represented.